Let me begin by reminding you of what I said yesterday. We're talking about n equals 2 theories, and I began with representation theory. So I talked about the little superalgebra, and the bosonic part of a massive little superalgebra is SO3 plus SU2 R symmetry. The basic representation of the little superalgebra is the hypermultiplet, which I'm denoting rho HH. There are two kinds of representations. I guess I should have put that here. There are two kinds of representations. The long representations, where the mass is greater than the central charge in absolute value. And they have this form, rho times some arbitrary representation of SO3 plus SU2R. And the short representations are rho tensor H. And those are the BPS representations where m is equal to z. And then we talked about how we have a family of theories. We're focusing on the Coulomb branch, B. And if we have a point U in B, then we have a one-particle Hilbert space, which as a representation, as a unitary representation of n equals 2, depends on U. And inside that one-particle Hilbert space is a distinguished subspace, the BPS subspace, the particle representations that saturate the BPS bound. Now, the other thing about this Coulomb branch is that at low energy, we have a rank R abelian gauge theory. And in n equals 2, we get a self-dual abelian gauge theory. So let me remind you of what that is. We have a symplectic lattice, capital gamma, of electric and magnetic charges. It has rank 2R. We can therefore make a symplectic vector space V here. And in order to formulate the theory, we endow it with a positive definite compatible complex structure I. And then our two-form field strength is in omega, is a two-form on space-time with values in V. Somebody got confused last time about the curly F being the prepotential. This has nothing to do with the prepotential, so I changed notation in the notes. And so our field strength is going to be boldface F like that. And we can impose a self-duality constraint, the Hodge star times the compatible complex structure squares to 1. So in fact, we can have self-dual or anti-self-dual here. It's flat. And then I ended by saying, well, if we choose a duality frame, alpha and beta are vectors spanning gamma. Then we can summarize the positive complex structure by a period matrix, tau ij, which is a symmetric complex matrix. The x's and the y's here are the real and imaginary parts, and the y is positive definite. And in that case, we can derive the self-duality equations from an action principle, which I wrote right here. Are there any questions about what I said last time? All right. Now, there's one thing I should have said last time when talking about the abelian gauge theory, and that is that we have this abelian gauge symmetry. So in particular, there are the global gauge transformations, and they act, again, on the Hilbert space of states. And so we have a representation of this compact group. And so we can decompose that representation in terms of irreducible representations. And that leads to a grading of the Hilbert space. H sub u is the direct sum of H sub u comma gamma, where gamma goes over capital gamma, because gamma, another way to think of it, is that these are the characters of the global gauge group. Okay. Now, what we really need to start with today are the constraints of supersymmetry. So I want to summarize the constraints of n equals 2 supersymmetry. You see, we know that a vector multiplet has the vector gauge fields, but there's also the fermions and the adjoint valued scalar fields. Okay, so we need to write Lagrangians for those. And I've just told you what the Lagrangian is for the gauge fields. I haven't yet told you how to determine that complex structure. Okay, and we know one thing. We know that at low energies, the action is still n equals 2 supersymmetric. So what constraints does n equals 2 supersymmetry impose? That's a complicated story, and we're not going to derive it here. What I'm going to do is I'm going to tell you the answer. Okay? So it turns out that the constraints of n equals 2 supersymmetry say,
what do you mean by a global gauge group?
well, there are, you know what a gauge transformation is, right? Okay. So if the gauge transformation is constant, that's a global symmetry of the theory, not a local symmetry. That's a true symmetry of the theory, and we can classify states by their representations of that true symmetry of the theory. That's what I mean.
So you take the part which is not dependent on space-time.
Exactly. So the gauge, so a gauge group, if the bundle is trivial, the group of all gauge transformations is the maps from space-time M into your compact group. Okay? So those are some g of x. So A goes to A, G equals G inverse AG plus G inverse DG. Okay. Now, inside of that is a copy of G, which are just the constant transformations. That copy of G has a different conceptual role to play in the theory. It's not a local gauge symmetry, it's a global gauge symmetry. It's a true symmetry of the theory, and we can classify states according to their representations of G. In this case, it's a little trickier because I'm using the self-dual formalism, so the G is rank 2R torus, and the characters, the irreducible representations of that compact torus is this lattice, capital gamma. Any other questions? Okay. Oh, no.
But sometimes, like say in QCD, the global color is not really
in the presence of monopoles. There are topological effects. Global color is not defined in the presence of monopoles, and there are interesting topological effects, but that won't bother us here. That's very much a non-abelian phenomenon. Okay, so back to the constraints of supersymmetry. So one thing it says is that there are local coordinates AI, where I goes from 1 to R, on B. So in particular, B is R complex dimensional, and a locally defined function, and here I do mean the prepotential, curly F, called the prepotential, which determines for us this complex structure by telling us what the tau ij is in some duality frame. So I've basically made a choice of duality frame in order to write the local coordinates, and then tau ij is d squared f by dai daj. And having done that, I therefore know what this Lagrangian is. These are now functions of the a's, and supersymmetry also tells me what the Lagrangian is for the a's. And it's that. Now I'm using A for two things. One is coordinates on B labeling the vacua. But of course, you see, you could make these low energy excitations where as you vary, as you go over space-time, the vacuum changes very, very slowly from point to point. So if I have these moduli coordinates here, that means I have a field AI of x mu, which can't vary too slowly if I'm in the low energy approximation, but it is a field in the low energy theory, and that's the Lagrangian for the field. Okay? So these are the vector multiplet scalars. And now the fermions are important, but I'm not going to write them down because we won't use them. Now the other thing that the constraints of n equals 2 supersymmetry give to you is a formula for the central charge function. Well, so far we have the central charge operator, Z, in the supersymmetry algebra, but it turns out that when we look at this operator Z hat acting on one of these graded components, Z hat being an operator in the supersymmetry algebra, Z hat acts as a scalar on H sub u gamma. So we call that scalar Z of gamma u, or sometimes I'll also write Z sub gamma of u and call it the central charge function. Okay, and in all the examples I know, the central charge function is linear in gamma. So it's Z of gamma 1 u plus Z of gamma 2 u. Now, mathematically, you might write Z is in Hom of gamma C. But Z is not an arbitrary linear transformation to C. If we write AI equals Z of alpha I u, then these are the same AIs I was referring to before. So we can get a set of local coordinates by choosing a duality basis and acting with Z on the alpha vectors. And then the non-trivial thing is that if I define a dual sub I to be Z of beta I and u, then this same prepotential gives me a dual I is the derivative of f with respect to AI. So in particular, it follows that tau ij is dAdi by dAj. Okay, so those are just the constraints of supersymmetry. So now I'll tell you what the Zyberg-Witten solution is. Okay, so what Zyberg and Witten did is give a prescription for how to determine this Z function, or equivalently this prepotential, as a function of u. And what they did is they said that there's a family of Riemann surfaces so I'll draw it this way. So there's a family of some Riemann surfaces, sigma sub u as a function of u. And that family will be endowed with another piece of data in a moment. And from that family, we get the necessary data that we need here as follows. Our symplectic lattice is the homology, the first homology lattice of H1. And the symplectic product is the intersection form. Now, the Zyberg-Witten curves, that's what these sigma u are called. The Zyberg-Witten curves are, in fact, non-compact Riemann surfaces, and so you should compactify in order to get a nice symplectic lattice. That's what the bar means. Now, the complex structure on sigma sub u implies 1 on V. If you like, the V is the universal cover of the Jacobian of the Riemann surface. A more down-to-earth way of thinking about it is that the tau ij is equal to the period matrix of the Riemann surface. And then finally, we have to say what Z is. Z sub gamma of u is equal to the integral around gamma of a meromorphic one form. So this is not just a Riemann surface, but it's a Riemann surface endowed with a meromorphic one form called the Ivors Witten differential. And so that's an extra piece of data that you have to specify to determine the theory. Okay, and so they gave, in the case of, they gave a prescription for how to determine this family of Riemann surfaces with meromorphic one form, and then by 1, 2, and 3, we get the data of the n equals 2 gauge theory. So let me give you an example of that, which was their first example, which is to take the Lie algebra to be SU2 with no flavor. And in this case, the Coulomb branch is just the complex plane. We can think of u as half the trace of phi squared. And then the family of Riemann surfaces, sigma u, is the set of T and V, such that lambda squared T plus 1 over T is V squared minus 2u. Lambda is the dynamical scale in the theory, and this is sitting inside C star times C. And the Ivors Witten differential in these coordinates is V dt over T. Okay, now, yeah, maybe I'll do it this way. So, a better way to look at this curve is the following. From this, you can learn that lambda squared is equal to capital lambda squared over t cubed plus 2u over t squared plus lambda squared over t dt squared. And you see lambda is a one form, so this defines some curve in T star of C, where C is in this case the punctured sphere. So it's a double covering. Now, if you try to solve for lambda, you still have a cut at t equals 0 and infinity, so you would resolve that cut by writing t equals s squared. And so there are actually going to be 4 branch points. What are the branch points? You see, think of this as a double covering of the t-plane. So for every t, you have 2 values of v, right? You just solve that quadratic equation. Easy enough, right? It's, let's put lambda to 1 by a rescaling, so it's t plus 2u plus 1 over t. So for every t, I have 2 values of v, so I have a double covering of the t plane, the punctured t plane. T is in C star, except when the 2 roots coincide. And the 2 roots coincide at v equals 0. Okay, so that means there are 2 branch points in the t plane, some here and here, something like that. And then we should take a double covering of that, so we actually get 4 branch points in the S plane. And you probably know that if you have 4 branch points, then what you get is an elliptic curve. So what we're describing here is a family of elliptic curves over U. And then if we choose some A cycle and B cycle, okay, then we can write A is, let me use capital A and B here, is the integral of lambda of capital A, and A dual is the integral over the B cycle of lambda. And that completely solves the theory. Now, there's a very important phenomenon that happens here. You see, where are the branch points? The branch points are at t equals minus u plus or minus the square root of u squared minus 1. Or u squared minus lambda squared if I put the lambda back in. Now, if I go to these special points, u equals, say, plus 1, or u equals minus 1, then what happens is the branch points collide. Okay? And if the branch points collide, that means that some cycle is pinching. Because the way you draw the cycles before they collide is you say you draw a little thing around there, and then that lifts to the double cover as a closed cycle on the elliptic curve. So that means that at this point, u equals plus 1, this elliptic curve degenerates like this. Some cycle, say the A cycle, is pinching. And some period, the A period, is going to 0 here. Now, what happens is if you try and analytically continue around a singular point, what you'll find is that you bring this torus around and you smoothly keep choosing A and B cycles. What you'll find when you come back is that the new B cycle looks like this. That's B prime. In other words, there's monodromy of the lattice of homology cycles as I go around this singular point. And reflected in that is the formula A dual is I over pi A log A. Okay? So one important lesson to learn from this is that so far I was just talking about a symplectic lattice, but you must bear in mind that that lattice can actually have monodromy around singular points in the u-plane. A final remark is that this particular form of the Ivors Witten curve fits in very well with a certain six-dimensional point of view on these theories, which I think might be covered in lectures of Davide Gaiato. Okay, so that's all I'm going to say about Ivors Witten theory. Obviously, there's much, much more to say. But we're focusing here on BPS states and their wall crossing. So let's get back to our problem of enumerating BPS states. Okay, understanding the BPS spectrum. Well, if we try and enumerate those BPS states, what are we trying to do? We're trying to pick out the BPS subsector from the one particle Hilbert space, H sub u up there. And, there are all sorts of long representation, and they have some mass, and their mass will depend on u, and it will depend on other parameters. Okay? And maybe this particle has some charge gamma, let's say. Well, in general, this will be bigger than z sub gamma of u, and then it will be a long representation, and we don't want to count it because its mass is complicated. It depends on all sorts of other parameters, in particular, for example, hypermultiplets and ways we cannot control by holomorphy. But it can happen that as we vary those other parameters, for example, hypermultiplet parameters, it can happen that m sub gamma of u is equal to z sub gamma of u. Well, then we saturate the BPS bound. Okay? Then we saturate the BPS bound. And so the long representation, rho times h, now really looks like a short representation, with an H prime, where the H prime is just rho half hypermultiplet times H. Looks like a BPS representation. Let's call those fake BPS representations. We want to find some kind of way of counting that discounts those kinds of fake BPS representations, and that also doesn't count the long representations. So what we're looking for is an index. We're looking for some function that vanishes on long representations, but doesn't vanish on true, if you like, short representations. OK, so now there's a nice index you can introduce. So if I have rho, a representation of my bosonic part of my little superalgebra, SO3 direct sum SU2R, I'll say its character, the character of rho, is the trace of x1 to the 2j3, x2 to the 2i3, where j3 is one of the generators of SO3, and i3 is one of the generators of SU2R. OK, so let's just calculate a few examples of this. So let's calculate rho of the half hypermultiplet. And so I hope you can see that that's equal to x1 plus x1 inverse plus x2 plus x2 inverse. Right? Rho half hypermultiplet is up there. It's 0 half plus 1 half 0. You can do that calculation in your head if you're following. OK, now if you also look at my formula for the long representation, we see that the character of a long representation is x1 plus x1 inverse plus x2 plus x2 inverse squared times the character of this h. And the character of a short representation is x1 plus x1 inverse plus x2 plus x2 inverse times the character of that h. OK, so now what we're going to do is we're going to specialize those characters in such a way as to write a function which vanishes on long representations and not on short representations. And while I erase the board, if you haven't studied the notes, you can try and give that some thought. How would you do that? Well, you want a 0, at least sometimes, which suggests that maybe you should take x1 equals minus x2. Now, if you take x1 equals minus x2, that's overdoing it, right? Because then both characters of long and short representations vanish. But you see, the long representations have a second order 0, and the short representations have a first order 0. So that suggests that we should consider x1 d by dx1 times this character of rho. And then we set x1 equals minus x2 equals, let's say, y. And so on the one hand, from the definition of the character, that's just trace of 2j3 minus 1 to the 2j3 minus y to the 2 curly j3, where curly j3 is straight j3 plus i3. OK? Now, look at it. If I take that derivative and then set x1 equals minus x2, this vanishes. Right? But this does not. So that's what I want. So that's equal to y minus y inverse times the character of this h at x1 equals minus x2 equals y. OK, that's an index, and we call that the protected spin character. Now, we use that name because it's not the spin character. The spin character would be just counting the trace of y to the 2j3. That doesn't vanish. Yes, sir?
It has J3 and I3, but they're from different algebras. Why do you do that?
Yeah, but you see, if I have a sum of two Lie algebras, okay, then I can make a representation of a common Lie algebra. Okay? I can make a representation of both of those by taking the generator J3 tensor 1, if you like, plus 1 tensor I3. No, yeah, you can always combine, yeah, generators like that. Okay. I didn't answer your question very well. Excuse me. You can't take SON and add generators of SON to E6. Maybe that was your question. But you see, SO3 and SU2R are isomorphic Lie algebras. Well, this is all I need. So SO3 and SU2R are isomorphic Lie algebras. So what I'm doing here is inside this direct sum, I'm taking a SU2 diagonal, okay, and I'm writing the generator, a generator for that diagonal sub-Lie algebra. All right, so now we've got this protected spin character. As I was saying, you cannot just take the spin character. That will not vanish on long representations. It will not vanish on these fake representations. It's not an index. But the trick here, which I only learned in the last year, is that you can do this when you have SU2R symmetry. Okay, in supergravity, you do not, in general, have that SU2R symmetry. Okay, now, we talked about the grading by the characters of the global gauge group, or by the electromagnetic charge lattice, if you like. And so we can apply that grading, in particular, to the BPS subspace. So that's graded by the charge lattice. And again, I don't know a fundamental reason for this, but in all examples, this is finite dimensional. If it weren't finite dimensional, the thermodynamics would be pretty sick. But in the examples, it's always finite dimensional, and therefore we can consider the well-defined object, the trace over the BPS space of 2j3 minus 1 to the 2j3 minus y to the 2 curly j3. And we can define the protected, actually, yeah, that's not quite the protected spin character. We pull out this factor of y minus y inverse, since it's always appearing, and we call the remainder the protected spin character. So it's getting carried away here. This is the protected spin character. All right. Yeah.
From the index, can we construct the representation?
Pardon?
Can we index, from the index, can we construct the representation uniquely?
Yeah, that's a nice question. The following is a true fact. A representation of SU2 is completely determined by its character. Okay? So what you can determine, okay, so this protected spin character is equal to the character on h sub gamma, little h sub gamma, evaluated x1 equals minus x2 equals y. And so from that, you can uniquely determine it as a representation of this diagonal SU2. But I think that's all. Oh, I don't think the minus sign should bother you. Okay, now as I was just stressing, you don't always have that SU2R symmetry around to help you, but you do always have the SO3 rotation symmetry. And so there's a further specialization of the protected spin character. At y equals -1, we get omega of gamma and u, which is called the BPS index. Okay? And this is an index. It's just a number. It's not a function of y, but it's an index, and it is available in supergravity as well as field theory. And it can be intrinsically defined, this is a little exercise for you, as half the trace over the BPS subspace of 2j3 squared minus 1 to the 2j3, and it has a name. It's called the second helicity supertrace. And in general, in these black hole entropy stories, people calculate various helicity supertraces. For n equals 4 supersymmetry, you have to put in some more powers of the j3 squared to get non-zero answers. Okay, now, one more thing to say. For a hypermultiplet, the contribution of a hypermultiplet in a BPS space to the protected spin character is +1, and for a vector multiplet, the contribution is y plus y inverse. And so if I specialize to the BPS index, that gives me +1 for a half hypermultiplet and -2 for a vector multiplet. All right. Now, these indices, being indices, are expected to be constant, and they are piecewise constant, but the whole point of these lectures is that they can change as a function of u discontinuously. And so now my next job is to start to show you the physical reason for how they can change. Okay? And to do that, I first need to talk a little bit about supersymmetric field configurations. Okay, so we've talked about BPS representations, okay? And we saw that there were some supersymmetries, the R supersymmetries, which annihilated some quantum state. Now there's an analog of this in the classical field theory. So remember, a state preserves a supersymmetry Q in general if Q annihilates it. And so therefore Q commutator O for any nice decent O will be 0 if that state preserves supersymmetry. And now we want to think of vacuum expectation values of O's for various fields as classical values of the fields. Some kind of coherent state formalism. Now, if O is a bosonic operator, then this is going to be a fermionic operator, and this psi is some kind of vacuum and is going to have some kind of Lorentz invariance, and so it will trivially vanish. But if we look at Q on a fermionic operator, then if you look at the supersymmetry transformation laws, on the right-hand side of the supersymmetry transformation laws, there are bosonic fields, of course, but there are derivatives of bosonic fields, typically first-order derivatives of bosonic fields. And so setting this to 0 is a certain differential equation on those bosonic fields. So those define, solutions of those first-order differential equations define what are called BPS field configurations. They're the semi-classical analogs of the BPS particles. So let's consider the BPS field configuration which is sourced by a dion of charge gamma of charge gamma with a phase z sub gamma of a BPS dion of charge gamma with phase e to the I alpha gamma absolute value of z gamma. Okay, so we saw at the particle level that we have these unbroken R supersymmetries with the zeta equals minus e to the I alpha gamma. And in the notes, I wrote down the supersymmetry transformation laws. So now it's a bit of an exercise, which I'm not going to do on the board, to write down what are these supersymmetric differential equations. And the answer, after a little bit of work, is that the vector multiplet fields, the fields have to be time independent, and F0L plus, in a duality frame I, is I d by dxl of the scalar phi I over zeta, where the F plus means F plus I Hodge star F. Okay, now that's a first order differential equation for the fields, and I'll indicate the solution. So the electromagnetic field created by a dion will look something like this. F upper I is 1/2 omega s times something in the unbroken Lie algebra times omega d times something in the unbroken Lie algebra. So these guys define vectors in the Cartan subalgebra of the spontaneous symmetry breaking. Omega sub s here is sine theta d theta d phi. It's the volume form on a sphere. So we have a sphere here, which is surrounding our BPS particle. Omega d is the four-dimensional Hodge dual on omega sub s, and so that's dr over r squared dt, where r is the radial distance from the particle. Okay. So we can simplify this equation a little bit, and we get twice d by dxl of phi I over zeta is d by dxl of 1 over r of rho mi minus I epsilon rho ei. And now the right thing to do here, this is a little tricky, the right thing to do here is to try and write these equations in a duality invariant way. Okay? So the duality invariant field strength, F, is 1/2 omega s tensor gamma s plus epsilon omega d tensor gamma d, where gamma d is that complex structure I applied to gamma s. Gamma s is the quantized charge. So the p's are magnetic charges and the q's are electric charges, and they're integral. Okay, so this gamma s is in capital gamma. The I is not in the lattice, right, because I is varying continuously. And and you can express the rho's and rho m and rho e's in terms of the p's and q's. In particular, the rho mi is pi. Now, in the notes, I made an exercise last night, and there where I guide you through some of this. This is actually a little tricky here. For example, here is an example, a very rare example, where you can solve the Q fixed point equations, the Q supersymmetry equations, and yet it's not a solution of the full second order equations of motion. A very unusual situation. Usually if you solve the Q fixed point equations, then you get a full solution of the equations of motion, but not here. So in particular, the rho E has to be determined by a formula you'll find in the notes in terms of the P and Q to satisfy the Maxwell equations. More to the point of what we need to do is the following. Okay, since rho M is quantized, it's independent of space, and so we can take the real part of this equation, you see, and we could say twice the real part. Actually, let me write that on the next board. We could say twice the real part of phi I over zeta is equal to pi over r plus a constant. And what's the constant? Well, the constant is clearly the value of phi at infinity, at r equals infinity. Okay? So that's partially the solution of this BPS field equations. Now, as I was saying, the right thing to do here is to make this duality invariant. Okay, and now that's a tricky story, which I detail in the notes, and let me just give you the answer. There's a problem I added last night in the notes where I guide you through how to make this duality invariant. You see, I've chosen a particular duality frame to write this. It's much better to write it this way. There we are, twice the imaginary part of zeta inverse z gamma of u of r is equal to the symplectic inner product of gamma with gamma c over r plus the value at infinity for all gamma and gamma. This is the analog of something called the attractor equations, which we'll be coming to shortly. Okay, so what's the net result? So what is the field configuration, the vector multiplet field configuration created by this dion here? It creates this spherically symmetric electric and magnetic field, and it makes the vector multiplets r-dependent. You see, this determines the values of the vector multiplet scalars as a function of r. So at infinity, we choose our vacuum. That's what I called little u. But now, in the presence of this dion, as you move in radially, the vector multiplet scalars that you see change. And that's going to be our key to showing that BPS particles can make BPS bound states. So that's the next thing I want to show you. So I'm first going to do it by an approximate calculation, because that calculation really shows the physics of what's going on, but it's only approximate, and then I'll give you the exact answer for the bound state radius. Okay, so the approximation I'm going to make is that this particle here that's creating this field is very heavy. So let's call its charge gamma c. That's c for core. And now what we're going to do is we have this very heavy particle, and we're going to put a little probe particle, tiny little probe particle of charge gamma h in the field of this dion. Okay? So the probe approximation says that this is much bigger than z of gamma h u. So what is the dynamics of this probe particle? Okay, well, the dynamics of a particle moving in an electromagnetic field is m ds, s is the proper time, plus gamma inner product A. This is a slight generalization of a formula I hope you all know. In the self-dual formalism, we use the self-dual A here. Okay, so we have the electric and magnetic charges dotted into the electric and magnetic potential. And we have the mass of the particle times its proper time. Okay? So this Lagrangian is a Lagrangian for my probe particle with charge gamma h. Now, it's a BPS. So we know the mass of this probe particle. The mass of this probe particle is z of gamma h, u, but what u? It depends on where the particle is, right? Because the vector multiplets are changing as a function of r. How are the vector multiplets changing as a function of r? They're changing by this equation right here. Okay? So we have this position-dependent mass and this electromagnetic field. And so straightforward to show that the energy is z of gamma h, energy of the particle at rest, minus gamma h times the Coulomb potential. And then another exercise in the notes shows that the Coulomb potential can be written as the symmetric inner product of the gamma h with the gamma c over 2r. Now, I think that's a really beautiful result. Remember that we had, from the compatible complex structure on our symplectic vector space, we automatically had a symmetric form, which we, for physical reasons, said had to be positive definite. That's that symmetric form coming back. And just think about it physically. Well, the Coulomb potential should be symmetric. It should be duality invariant. And if you have the same charges, it should be positive definite, right? It should be repulsive. So it sort of has to be that. Now, there's, if I took the real part of these equations up here to get this equation here, if I similarly take the imaginary part and make it duality invariant, again, details are in the notes, then you can find that twice the real part of zeta inverse of gamma h u of r now is equal to this symmetric form plus the value at infinity. Okay, so now we can substitute, we can solve for this. And so we get that the energy of the probe particle is the mass, the position-dependent mass, times, well, you can do this in your head. It's 1 minus the cosine of alpha h of r minus alpha c, and then a constant at infinity, minus the real part of z gamma h of u over zeta. Where alpha h of r is what? Well, you see, z of gamma h and u of r has a phase, e to the I alpha h of r times the absolute value. So that means that our potential energy has a shape roughly like this. It's as a function of r, it has some minimum and it goes back up. And where is it minimized? It's minimized when alpha h of r is equal to alpha c. Notice that that's exactly the place where the central charges of the probe and the central particle are parallel. So that means z sub gamma h is parallel to z sub gamma c. So that really shows you that this BPS particle can bind to this BPS dion. Now, in fact, that bound state is a BPS bound state. And we're not going to show the details of that here, you can analyze the supersymmetric quantum mechanics of this particle and really show that at this radius you've got a minimum and a supersymmetry is preserved. But there's something that might bother you about this. Oh, I almost forgot the most important thing. What is the value of the radius? Okay, so what is the value of this bound state radius? Well, okay, so alpha h of r is alpha c. So the central charges are parallel. So let's put gamma h here. Okay, and we have a gamma h here. And so at the bound state radius, this is 0. Because zeta is minus e to the I alpha c. So these are parallel, anti-parallel actually, complex numbers. Their imaginary part is 0. So that means that this is equal to 0. And so we solve, and we get that the bound state radius, R12, is 1/2 gamma h, gamma c, 1 over the imaginary part of z gamma h, e to the minus I alpha c, where this z gamma h is evaluated on the vacuum moduli at infinity. So that's the formula for the bound state radius. But now it should bother you. Is anybody bothered? Well, while I'm waiting for you to get bothered, I'll take the opportunity to erase the blackboards. There's something physically a little funny about this formula. Could. Yeah, that's one thing, but that's not what I'm looking at. I'm going to be talking about the possible negativity of that in just a moment. That's a very good point. But there's something else. Pardon? The imaginary part might be 0. I'm coming to that too. But let's say it's positive, and let's say the imaginary part is not 0. There's still something wrong with it. Hint, it's because I derived it in the probe approximation. So what am I saying? I'm saying that I have these two BPS particles with charges gamma c and gamma h. And I'm telling you that they form a BPS bound state. And I'm giving you a radius, the bound state radius for that bound state.
Not symmetric.
Yeah. It's not symmetric. That's not physically reasonable. If I'm not in the, it's reasonable in the bound state, in the probe approximation, of course, because probe approximation broke the symmetry. But my basic problem of saying I have two BPS particles of charges gamma 1 and gamma 2, and I'm telling you they make a BPS bound state of some radius, well, it better be symmetric in gamma 1 and gamma 2. So the true formula, which we derive from the multi-centered solutions of supergravity, which I guess I have 15 minutes, so I think maybe we'll be doing that tomorrow. The true formula, the exact formula, has R12 equals 1/2 gamma 1 gamma 2 times z of gamma 1u plus z of gamma 2u over the imaginary part of z1, z2 bar. And this rather beautiful formula is due to Frederick Denef. Now let me make some comments about it. First of all, yep.
You mentioned that where the bounce, the minimal potential is that the two central charges are parallel. So should the alpha c, I mean, should we not take alpha c as a function of r as well?
No, because I'm in the probe approximation again. I just said I have a particle, a heavy particle of charge gamma c, and then it had a BPS, it had a central charge of, e to the I alpha c gamma c. And so then I said those are the unbroken supersymmetries for that fixed zeta equals e minus e to the I alpha c, and I wrote down the field configuration for that fixed zeta. So zeta is fixed, so alpha c is just a constant, not a function of r. Now, in the mythical third lecture in which I would have talked about so-called line operators in n equals 2 supersymmetry theories, I say mythical because it's obvious I'm not going to get to it. In that mythical lecture, I would have introduced these line operators which had a fixed zeta. And it's one of the reasons I'm doing things in this way. Okay, back to Denef's formula. Now, supposing we're in the probe approximation where z of gamma 2 and u is much, much greater than z of gamma 1 and u. Okay, that was the probe approximation. Then you can check that this formula reduces to the one we derived because, you see, one way of writing this formula is that this is 1/2 gamma 1 gamma 2, 1 over the imaginary part of z1 e to the minus I alpha, where alpha is the phase of z1 plus z2. But in that limit, where we have the probe approximation valid, that phase becomes the phase alpha c. Okay, so that's the first remark. The second is that this can be derived from the multi-centered solutions of supergravity. I'll indicate that next time. And the third is, as has already been pointed out, while this is symmetric, it might not be positive. And that determines what I call the Denef stability condition, which says that this kind of bound state, can only form if gamma 1, gamma 2 times the imaginary part of z gamma 1 u, z gamma 2 u is positive. Okay? So that's a condition. If I fix gamma 1 and gamma 2, that's a condition on u. It might be true for some values of u. It might be not true. Okay, so we'll come back to this in a second. Now, supposing we have one of these bound states. Okay? How do we know that it can't decay? I mean, maybe it's locally stable. Maybe it's a metastable state. Well, how do we know that it can't decay? Well, the answer is that this bound state is itself BPS. So the binding energy is z of gamma 1 plus gamma 2 and u minus z of gamma 1 and u minus z of gamma 2 and u. Now z1 and z2, these are complex numbers. So for example, if, this is a useful remark for what we'll do next time, if z1, z2 bar is greater than 0, what does that mean about these complex numbers? It means that z1 is counterclockwise to z2 with an angle between it which is less than pi. Okay? And by the triangle inequality, this is less than 0. And so that means that there's negative binding energy. And that means, no, they can't tunnel out to particles which are out at infinity. BPS particles out at infinity will at least have this much energy. So this binding energy is 0, with one very significant exception, which I trust you all see. The exception comes except when Z1 is parallel to Z2. Okay? When Z1 is parallel to Z2, this is actually equal to 0. And that is a place where this thing might decay. So that defines what's called the wall of marginal stability, which we associate to a pair of charges, which is the set of points u and b, such that 0 is less than z of gamma 1 u over z of gamma 2 u is less than infinity. That's the wall of marginal stability. Okay, so now we finally come to what was to have been the conclusion of lecture 1, which is the primitive wall-crossing formula. So supposing we have in this room one of these bound states of gamma 1 and gamma 2. Okay? And we have this boundary condition u at infinity, which is clearly going to be satisfying the Denef stable condition, right? Because we've got the bound state. Now, supposing there's some experimentalist out at infinity, I don't know, Piscataway, New Jersey, okay? The experimentalist is in Piscataway, New Jersey, and dials the moduli. It has a moduli, he or she has a moduli dialing machine. And that experimentalist starts dialing the moduli. And so here's the wall of marginal stability. Okay, and here's this u in a Denef stable region, and the moduli start moving till they hit some u marginal stability. So what's going to happen to the central charges? Well, the central charge is going to be, say, like this. That's going to be true if gamma 1 inner product gamma 2 is positive, then the imaginary part is positive. And as we hit the wall of marginal stability, Z1 and Z2 become parallel. And as somebody observed, that means that the imaginary part in the denominator goes to 0. And that means that the bound state radius goes to infinity. And that means that this bound state is leaving the Hilbert space. So we're here, the experimentalist out at infinity is dialing the moduli, and the particles just move apart and go off to infinity and leave the Hilbert space. So our BPS Hilbert space changed as we crossed the wall. Okay? And now we want to know how much did it change? Well, there is where our indices come in. So how much did our BPS state change? Well, our bound state looks like this. We have gamma 1 and gamma 2. So we have a Hilbert space for gamma 1, BPS Hilbert space u of gamma 1, and BPS Hilbert space of u of gamma 2, because these particles might have internal substructure. And remember that in the field of these dions, we have an electromagnetic field, which itself has degrees of freedom. And so we should tensor J gamma 1 gamma 2 like that, where J means the following. J is the representation of SO3 rotations of dimension 2j plus 1. And in the exercise, as is in the notes, I ask you to calculate this. Now, classically, what you will get is 1/2 gamma 1 minus gamma 1 gamma 2. And then there's a quantum mechanical effect, which I don't explain, but which can be explained by thinking about the supersymmetric quantum mechanics of this probe particle, which gives it -1. Okay, so this is the exact formula for the spin carried by this system. Now we lose all these states as this radius R12 goes to infinity. And so the change in the protected spin character is, well, we lose it, so I guess there's a minus sign there. We get the character of rho sub, we get the character of j sub gamma 1 gamma 2 of y times the protected spin character of gamma 1 u y and omega of, didn't leave myself enough room, times omega of gamma 2 u and y. Now, these might themselves have wall crossing, so I should actually say where I'm evaluating this index. So I'm evaluating it at the marginal stability point where I'm crossing, and I'm assuming here a few things. One thing I'm assuming is that I'm crossing a generic point on the wall of marginal stability. And another thing I'm assuming is that gamma 1 and gamma 2 are primitive. That means that they are not multiples of other quantized charge vectors. That's why it's called the primitive wall crossing formula. And in the last 2 minutes, let me illustrate why that's an important assumption. So let's return to the SU2 Ivors-Witten theory that we talked about before. And I showed you that there was a U-plane and there were two singular points in the U-plane where the two branch points coalesced at u equals lambda squared and u equals minus lambda squared. And I showed you that there's monodromy on that charge lattice. What is the charge lattice? The charge lattice, gamma u, in this case is rank 2. So it's just a symplectic lattice on z1, z plus z. It has monodromy as we go around here. It has monodromy as we go around here. And so we should choose cuts to trivialize that monodromy. Okay, now I also showed that there's a charge z of gamma 1, which goes to 0 here. And there's a charge z of gamma 2, which goes to 0 here. These are called the monopoles and the dions. And you can show that gamma 1 inner product gamma 2 is 2. And now, once we've chosen those cuts, we can trivialize our local system. And so if we call this one A, this one AD, it turns out that these charges are populated. That means there are BPS states with those charges. And now we can ask about their wall of marginal stability. And so the wall of marginal stability looks like this. It's not an exact circle, but it's something roughly like a circle. So the wall of marginal stability separates the U-plane into a strong coupling region and a weak coupling region. And then by monodromy, there are actually two weak coupling regions if you choose cuts, but they're trivially related by monodromy. And now by ad hoc arguments, Zyberg and Witten, and then later Bilal and Ferrari more rigorously, determined exactly the BPS spectrum. So I told you in the last lecture that in general the BPS spectrum is not known. But in this particular case it is known. And so we have hypermultiplets for gamma equals plus or minus gamma 1, gamma 2, and 0 for all other charges. But in the weak, this is for you in the strong coupling region, but H gamma BPS is more complicated in the weak coupling region. It looks like this. And this. For you in the weak coupling region. Okay. So you see there's a very dramatic illustration of wall crossing in the BPS spectrum. There are only some 4 states here, finite number of states here. But out here, there's this infinite set of states. Our primitive wall crossing formula can deal with this case, gamma 1 plus gamma 2. This is a vector particle, you notice. So a very dramatic aspect of the Ivors-Witten physics is that the W boson in this theory is actually a bound state of a monopole and a dion. Very unusual. And, but then there are all these other decays. There's this infinite tower of dionic hypermultiplets. And you notice that they're not primitive. Okay? So next time, I'm going to tell you about the wall crossing formula that takes into account this non-primitivity. We'll first talk about something called the semi-primitive wall crossing formula, and then we'll show how that semi-primitive wall crossing formula allows you to derive the Kontsevich-Soibelman wall crossing formula, which accounts for the full wall crossing effects. Yes?
Do you have physical interpretation of delta omega there?
What's physical quantity that is corresponds to?
Well, I thought that was the point of this lecture. I mean, I defined omega. I defined omega as the protected spin character, and I've given you a physical mechanism by which it changes. I don't know what.
The states that change or count?
Yes, absolutely. So we're losing this part of the Hilbert space, right? Because the radius is going to infinity. So we're losing those states. So the delta omega is the change in the protected spin characters of the BPS states, and that's what we're losing. That's what the wall crossing formula says.
That's a physical number of states.
Well, it's, as I said, you have to calculate an index. Because if you just try and calculate absolute numbers of states, it won't behave very well. It will jump in all sorts of ways. The nice thing about the index is that it's constant. It's piecewise constant. Yes?
Where did you use the primitivity?
Because I assumed that this is the only kind of bound state configuration. So if gamma 1 is not primitive, then there can be much more complicated, as you'll see next time, there can be much more complicated bound state configurations with the same total charge. Okay, and so they will affect the wall crossing.
But a non-primitive, I mean, like a bound state of that kind, n gamma 1 plus n gamma 2.
Yeah.
In general, so the statement is we won't know what would happen.
It's a more complicated, if I draw physical pictures for these bound states and try and give these arguments that some bound state radius is going to infinity, they're more complicated configurations.
But this particular one will be, right?
Well, it must be true because the Kontsevich-Soibelman wall crossing formula is more complicated.
From this argument.
Sorry?
From the arguments that you made.
So from the argument I'm making here, I'm saying that the only kind of bound states look like that. What I'm saying, if gamma 1 is not primitive, I replace it by n gamma 1. You see, if I take n gamma 1, I might have a particle like this. Okay, but I might also have some other bound state with the same total charge like that, where there are n of those. That will contribute You see, my BPS space is just the BPS configurations with a certain total charge. I haven't taken into account those kinds of charge, those kinds of states. That's the problem. Yes, sir.
You were talking about we're considering only one particle BPS Hilbert space.
Yes.
But this bound state seem composing two particles.
Yeah, but it's. I mean, you think of a molecule as a particle, a single particle, right? It's like that. So it's really bound together and making one particle. There is a continuum. So I mean, if I have two particles, right, I can have a continuum, but then I can have a bound state, which is separated from the continuum in the energy spectrum, and I treat that as a single particle. Yes, sir?
Sorry, could you explain again why the mass varies with position of the
Why the mass varies with position. You mean back in the probe discussion? Okay. So I had a heavy particle of charge gamma c, and then it produced some fields. Okay? Now, it's obvious that it produces an electromagnetic field. But then I showed that because we were looking at a BPS field configuration, the vector multiplet scalars also have to change. So the U is a function of R, and I wrote some explicit formula that determines it, something called the attractor equation. Now I put this probe particle, gamma h, in here. Now what's the mass of a BPS particle? The mass of the BPS particle is z of gamma h of u. But what u? It matters what the local value of u is. And that u is varying with time, the space. Okay? Yeah. Yeah.
The wall of marginal self-stability you always associate with two primitive vectors only, right?
That's the beginning of my next lecture, but I'll simply say it right now. You see, the wall of marginal stability is clearly the same as the wall of the marginal stability of n1 gamma 1, n2 gamma 2, if n1 and n2 have the same sign. So this is again a reason that the primitive wall crossing formula is only part of the story. I'm just saying what I'm going to say at the beginning of next lecture. It's why the primitive wall crossing formula is only part of the story. There can be complicated bound states of these kinds too, and they will also decay, or not, as we cross walls of marginal stability, the same wall. So something much more complicated is happening as we cross that wall, and that's what I'm going to try and describe to you tomorrow.